It's time now to confirm our findings using statistics. And in a nutshell, the role of statistics is to rule out the possibility that the results we have obtained or the conclusions we have formed are actually based on or due to a random influence, such as chance, random errors, sampling errors, etc. In our earlier analysis, we have explored the relationship between different variables and made several assumptions along the way. For example, when we used to test numeric variables against each other to understand how different variables relate or move together, we used correlation. And we noted that there is some sort of a relationship between different variables and targeted value or targeted variable being insurance charge. How significant is this relationship? In terms of statistical testing, we have two assumptions or claims that we want to validate. These assumptions are known to be hypotheses. And there are two types of hypotheses. There is the null hypothesis and the alternative hypothesis. Coefficient of correlation measures the relationship between two variables. One of the hypotheses that we can claim is that there is no relationship between the two variables. For example, there is no relationship between insurance charge and age. This no relationship hypothesis is called null hypothesis. Another claim that we can make, or the counterclaim of our null hypothesis, is that there is in fact a relationship between the two variables, and we refer to it as an alternative hypothesis. The question is, how can we choose between these two hypotheses, or how can we test these two hypotheses? Simply by running an experiment. So for example, in Pearson correlation, we want to know how significant is this 0.30 in terms of relationship between age and charges. In other words, is it statistically significant to say that there is an actual relationship between the two variables, or it is just due to a random chance or error? One way to think of it is that if we used another sample than the one that we used to run this test, are we likely to get the same correlation coefficient or not? This is what statistical significance means, and this is what statistics role is about, to rule out the possibility that the results we obtain from whatever test we do is due to random error or chance. So, as a rule of thumb, when doing any type of statistical test, we need to know two main things: the null hypothesis and the alternative hypothesis. Let's run our first statistical test for Pearson correlation. To do this, we need to import the modules that enables us to do statistical analysis. In Python, there are several modules. We are going to use SciPy. We can see here that R is almost 30, like we have seen here, and the p-value is a very small number. This is called scientific notation, and negative 29 means that you need to add before this number 0.29 times. So to lessen this number, we can use round. So we can see here that the numbers became smaller, and because we said it was negative 29 zeros, it rounds to almost 0. Now, what does P stands for, and what does 0 means? Think of P as the probability of something. Okay, what does this mean in terms of statistical significance? We said that for Pearson correlation, our null hypothesis is that there is no relationship between the two variables, and our alternative hypothesis is that there is in fact a relationship between the two variables. The role of P value is to enable us to take a decision whether to accept the null hypothesis and conclude that there is actually no relationship, or the other way around. The value of P determines the directions we should use. So if we have a P smaller than 5%, and we will talk about 5% later, we can say that we are confident that this result, this 29, is statistically significant to support the alternative hypothesis. In other words, we can reject the null hypothesis, being that there is no relationship between the two variables, and conclude that there is actual relationship between the variables. So p-value is our compass, and it depicts the significance of the results we've seen, and significance in terms of accepting or rejecting the null hypothesis. If we want to do this for all numeric columns, we can simply iterate over all the columns and do this calculation, and this is where what we have discussed in coding tutorial comes in handy. We are going to do a for loop, collect the RMP for each column, then display it in a sort of table. So we basically iterate over all the numeric columns, run the calculation, and of course we change the age to be the column, then append the result to the list. In order to append multiple results, we use tuple. So we're gonna R and P. Okay, let's look at correlation. We here see that it consists of the correlation coefficient, it corresponds to what we have calculated earlier, and the related p-value. We can go a step further and create a data frame or a table from this results using pandas. Simply pass pd. We pass the correlation, and let's name columns to be correlation coefficient and p-value. Here we see it's displayed instead of this list of tuples, it's displayed in a nice table. We can also use round to be more readable. So we round this to round it to the nearest 2, and p-value to the nearest 5. Okay. Ignore this one because this is charge against charge. We don't need it. We can actually drop it. So we have the same exact coefficients and their related p-value. To understand hypothesis testing and p-values, let's run a small example. We know from earlier that gender is almost equally distributed, so the dataset is balanced between males and females. And if we want to observe whether this feature, the gender feature, has an impact on charge calculation, we can make hypothesis testing revolving around this. Let's first start by observing the change in mean across the levels of this category, being the gender. To do this, we will group the data by gender, and we want to observe the charges across each level of this grouped category. So we will simply group by charge mean, and here we can observe a small difference between the mean of the two groups. In order to quantify this, we can use the same code, but use diff, and diff will subtract this number from the above one, and so on. Okay, we have a difference of almost 1.3k between the mean of each two groups, and let's build our hypothesis around this. So we already said that there is two types of hypothesis, or two types of claims that we want to validate in each test we do, being the null and alternative hypothesis. So our null hypothesis will be that the difference across the means of the two groups is around 1.5k, and the alternative hypothesis will be that's not equal 1.5k. Okay, we are ready to proceed with our experiment. Let's first grab sample from each category and observe the difference between them. So in order to select a sample from a data frame, we simply say df.sample and specify the portion of the sample we want to collect. We will use a half of the data, so 0.5, which represents 50%, and replace equal true. Replace equal true here means that rows are allowed to be used twice in the sample, so we can have the same exact sample twice. We can run the code as is, but in order for you to replicate what we are doing here, we are gonna fix a random seed so that the result we observe now can be replicated in the future. What does this portion of the code really do? When we start taking samples from the data frame, it goes selecting samples randomly, and this ensures that the randomness in the operation has a fixed starting point. So each time this code is run, it will start from the same exact point it was initiated with. So if I run this code here and you run this code on your PC, we will get the same exact results. Let's see what this actually do. Okay, so we have a sample of 670 rows. Let's group by and observe the difference. And we can see here that the mean across each group is slightly different. So for males, it's 1.5K, and in the original dataset, it was 1.3K, and for female it's 1.2K and 1.2K. So what actually is this doing? It is selecting a sample and observing the mean across this sample. And if you recall, the main aim of statistical analysis is to rule out the possibility that what we are seeing is due to random error or chance. So the idea of what are we doing here is that if you hypothesize the difference between the two mean is almost 1.5K, and we select a random sample from the dataset, we should be seeing the same difference across this other sample. Otherwise, the null hypothesis, which is 1.5K, is not valid, so we can reject it and accept that the difference between the two groups is actually more than or less than 1.5K. Okay, so we have our first sample here, and let's select the first row. So we have female, and let's make another one for males. And males, let's see what this actually do. This selects the first value printed, and this one will select the second one. And we know that it displays first the female, then the male, so we can call this female, and this to be male. Let's calculate the difference between the two means, and we will name this observed difference equal male minus female, and know that this is actually the difference between the two means. And let's see, our observed difference is almost 3K. So let's repeat this process over and over again in order to test whether what we have seen here, the observed difference, actually is valid or not. And this will make sense in a few. So we are gonna make an empty list first to collect all the differences between the sample, and we are gonna loop. So we say for whatever, I don't really care about the name of the alias that we'll be using. We're gonna run our experiments for 10,000 times. So we'll do this selection of sample 10,000 times. But this time, we are not gonna fix a random state, because as we already understand that fixing the random state will reproduce the same sample over and over again, and we actually want each time this loop iterates or executes, we want to have a different sample. So by this, we ensure that each time the loop runs, a completely new sample is generated. Okay, and let's append to our list the difference between the two means. Let's run this. This difference list contains all the differences between the mean of the selected sample. So we actually have a distribution of all the differences across all these samples, and we can plot this distribution. So we can see here a normally distributed differences between the mean value of male and female, and we can actually see that the bulk of the distribution is centered around 1 to 1.5K, which is our null hypothesis. So this distribution represents our null hypothesis. If we want to test whether this statistic, our observed difference statistic, which is 3K, came from this distribution, we can simply plot the statistics. So plt.ax v line. Ax v line plots a horizontal line across the figure, and we are gonna plot the observed difference, and let's give it a red color, so color equal red. We can see this is where our observed statistic, or the mean of the sample that we have selected earlier, lies. It is outside the bulk of the distribution, actually at the tail of the distribution. So if we want to assess whether this calculated statistic of 3k is statistically significant to reject the null hypothesis for this specific sample, we need to calculate a significance threshold or significance probability, or the p-value. P-value will simply identify whether this statistic came from this distribution or no. So if we calculate how many observation in this distribution is actually greater than the calculated statistic in our sample, we can simply say that diff greater than observed diff. Okay, and this will create a Boolean index, and this Boolean index simply indicates that for each value in the difference list, and each value is represented by bars here in this distribution, whether each value is actually greater than our observed difference. We can see here that it's false, 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 and because of truncation we can see all the results, but if we calculate the mean, it will produce 0.04. What does this 0.04 means? It means that the proportion of observations in this distribution which represents the null hypothesis that is actually greater than the calculated statistics is 4%. So it means that only this portion from this line, 3k to 5k, are what is actually greater than this statistic. So it highlights that there is a small probability that this line actually came from this distribution, because if it came from this distribution, this line should be lying around here, around the center of the distribution. So like, for example, here, here, or here. But if only a small portion of the distribution is greater than what we observe, this means that this statistic does not really come from this distribution, and we can reject the null hypothesis. I hope this makes sense and it gets the message across. What does p-value mean, or what does the null distribution mean, and what actually we are trying to do with comparing the calculated statistic to a given distribution and observing whether it actually came from this distribution or not. So in a nutshell, if we have a statistic or a p-value that is smaller than a selected significant threshold, this means that the observed statistic is did not come from the distribution that supports the null hypothesis, and thus we can safely disregard the null hypothesis and accept the alternative hypothesis. We can use the same example to discuss an interesting theory known as Central Limit Theorem. The theorem basically states that with large enough sample size, the sampling distribution tends to be normally distributed. Let's first look at the distribution of charges. And we can see that charges is not normally distributed. It is actually positively skewed. And we saw earlier that when we took sample from charges and calculated the difference between the two gender groups, each sample we take and the corresponding mean that we calculate at the end forms a distribution of possible values that the mean of the two genders, or the difference between the two genders, mean lies. This is the sampling distribution. We noted that the difference between these two groups tends to be normally distributed, and this is actually what is known as Central Limit Theorem. How large should the sample size be? So the Central Limit Theorem kicks in. Actually, let's try this out. This is the loop that we have used to take different samples, and we used to iterate 10,000 times. Now let's decrease it to 10 times only, and we have not fixed random state to change the sample each time this iteration or this loop executes. We can leave it as is or fix a random state based on the number of iterations, so it will basically give the same result. So let's do this time. and plot the difference. The sampling distribution is not actually normally distributed. If we increase the sample size to, for example, 30, now it looks like it is actually normally distributed. So textbooks refer to the optimal number or the minimum or this threshold number where the central limit theorem kicks in to be 30. Now if we increase, let's say 400, rerun, the distribution is still normally distributed. Now let's run for 1000 times. Now it clearly looks like a normal distribution. So what does this says, or what does this proves, is that regardless of the original distribution, which is not normally distributed, if you have enough sample size, the sampling distribution tends to be normally distributed. And what does this mean, or how is this helpful? Some statistical tests that we run assumes normality in the data, and if your data is not normally distributed but actually you have enough sample size, you can get away with the normality assumption relying on the central limit theorem as we saw here. So what about trend lines? We have previously fitted these lines and said that they represent the relationship, or they capture the relationship between the two plotted variables in a sort of a formula. This plots as is does not convey this much. What we can do is we can actually calculate this formula by ourselves using regression models, and this will be a very light discussion of regression model. We are going to have a specific dedicated videos on modeling using regression and the inner working of a regression model and how are the calculations exactly made. So to build a model, let's import the modules for that. We're going to use the stats model for this, and SM is the alias for stats model. So we are here basically looping over the numeric columns and plotting the joint plots along with the fitted regulation line. What we are gonna do next is that we are gonna actually fit a model and estimate the parameters or the actual formula of this line. So we'll call our model to be, we'll pass the dependent variable being charges, the independent variable being the column that we plot, and we will add a constant. This constant is to facilitate the calculation of the coefficients, and don't worry much about this calculation for now because we are going to discuss it in details in another video. Next, we want to fit this model to the data, and fitting is where the calculations are made and actual coefficients are calculated, so dot fit. So by this line we are actually building a linear model using a single variable being whatever is in numeric column. So for example, the first plot, the regression model will be based on age. The second one will be based on BMI, so on and so forth. So it's just one single variable versus the dependent variable, which is being charges. Okay, so we have our model ready, but actually we still want to extract information from that model and add it to the plot. To do this, we can use format string method like we did in our coding tutorial earlier. So we'll name our text to be F, stands for format string. Then let's add our formula to the plot. So it will be y, which is a dependent variable, or actually charges, equal the intercept, and model.params. Params are the coefficients calculated from this model. The first param is the intercept, and intercept is basically the amount of charges when age or whatever the variable is 0. So params 1, and let's round it. And let's add the coefficient of an actual variable. So it will be model the params and 0. The first parameter is for the coefficient or the slope of the line, and slope is how much of that variable actually influence the dependent variable. And let's round it also. Okay, we have this and this. Let's put x here. X stands for the variable itself, and let's print on a new line. Additionally, let's include the r squared, and r squared stands for coefficient of determination. It's basically a measure of how good the fit is. It's actually one of the measurements and not an absolute measure of how good this model is, but it gives a flavor or an indication of how good this model really is. So it will be r squared. This backslash here just indicate that this code has a continuation, and this continuation is going to be in the following line. Next, we are going to use the p-value. And the p-value is just what we've discussed earlier. It is how significant is the calculation of these coefficients. And lastly, we calculate a skew score. And skew score, if you remember, when we said that charges is positively skewed, we want to quantify this skew because we want to know which variable might be problematic later on when you start building actual models. Skew score has a measure between -1 and 1. This is the rule of thumb that a normal skew score lies between -1 and 1. Anything above this is considered to be problematic and need to be dealt with, as we will see later. So let's calculate the skew score for each variable that we regress against charges. Let's actually add this text to the plot. So first we build the model, then we collect the parameters of the model, and then we plot. Lastly, we add this text to the plot. So let's give our plot variable name named axis and ax. This is how to add text to the plot. These are the coordinates of the text to appear next to the plot, somewhere here. So you specify the coordinates there. This is the x and y coordinate. Let's pass the text. Text will be this variable. It's called text. This is just basically modification for the plotted text. So now we're ready to plot our figure with these new additions. Okay. This is actually the formula for each line. So for this line we have an intercept of 3k, which means that if age is 0, we'd expect that charges be 3k plus the coefficient of age variable 257 means that for every 1 year increase in age, we'd expect charges to increase by 257. Let's look at BMI. And note that these models are separate models, and each model is built using a single variable. So for BMI, we say that the intercept is almost 1.2k, which means that if BMI is 0, we expect charges to be 1.2k, and for every increase in 1 unit of BMI, we expect charges to increase by 394 units. So if charges in USD, it will be USD increase in charges. Okay. What are these other three statistics? R-square is the percentage of explained variance in charges using this variable. So we say that age explains about 10% of variability in charges. BMI explains about 5% of variability in charges, and so on. Of course, these are very minor values. They basically state that these variables separately or independently does not significantly explain the variance in charges. Okay, the p-value of this calculated statistic indicates whether this calculated coefficient is significant or not. Of course, this is far from correct, because as we will see later, linear models has set of assumptions that needs to be validated before we can actually rely on any of these numbers. What we are actually doing here is that we want to just get an understanding or a flavor of what does this figure really represent. Lastly is the skew score, and we can see here the skew score is calculated for the top histogram, and the top histogram relates to the age, and we can see that age is uniformly distributed, so it has a very low score. Similarly to BMI, BMI is normally distributed, it has a skew score of 0.28, and so on. So when it comes to modeling, we know that there is no major issue with BMI and age in terms of skewness. We have already noted this and saw this in the histograms, but sometimes it is better to back up your histogram with such scoring. If you recall, when we analyzed the relationship between categorical features, we used crosstabs, and the main aim of crosstab is to understand whether one categorical feature depends on the other. We've noted that smoker is somewhat dependent on gender, as that most smokers were male, but for other two variables against each other, there was no visible or significant relationship. For example, region against smoker, we know that smoker groups are equally distributed across different regions, except for southeast region. It had the most or slightly higher significant smoker percentage, and this was due to the fact that there are more males in this region than in any other region. Let's first identify the significance of dependence between each of the groups. So we want to compare pairs of groups together, and in order to do this, we are gonna use combination. Combinations allow us to make pairs of whatever data passed to it without repetition. To understand this, let's first import combination. Combinations, then pass the cat columns and specify that we want two pairs only of each comparison. Let's look at the result. Okay, the first comparison will be between gender and smoker, then gender and region, and lastly smoker and region. We see here that it did not make repetitions, it only made this comparison between each two categorical feature once. Okay, so for each comp in combination, let's run our statistical dependence test between two categorical features. This is a chi-square test. It accepts a crosstab data form. So first we need to create a crosstab. So for this crosstab, it will be dfcomp0. And what is dfcomp0? If we take this first combination, for example, it will be gender and dfcomp1. dfcomp1 is the smoker. Then we calculate our statistic. It will be the chi-square and p, the related p-value, and it resides in stats model. Yeah, contingency. Pass our. Okay. And let's print the statistic and the related p-value. We can here observe the calculated statistic being chi-square and the related p-value. We are actually not interested in the statistic itself, but in the related p-value, and we can see that for the first comparison, It's significant because we are actually looking for a 5% significance threshold, and it's 0.007. For this, it is not significant, and for this also. So what does significant or not significant mean here? Remember when we said that the most important thing is to understand what is the null and the alternative hypothesis that this test is trying to achieve? The null hypothesis is that both categorical values are independent, so they do not affect each other, and the alternative hypothesis is that they are actually dependent, so one depends on the other. Okay, so when we have a significant p-value, we reject the null hypothesis that they are independent and accept the alternative hypothesis that they are actually dependent. So let's put these figures into a table like we did earlier. So let's establish an empty list to collect the results. So cross tab, or see, let's call it cross res, or let's give it any name. So just an empty list to collect. And instead of appending the statistic and related p-value only, we will also append the features that we compared against each other. Okay, so our list will consist of the two features, then the related statistic and significance threshold. Lastly, we just put it in a table. So pd.data frame, it will be this list, and let's name the columns like feat 1, for example, feat 2, chi-square, and p-value. Okay. What's interesting to observe here is that for the first group and the last group, the chi statistic is almost equal, but the p-value is different. We can see here that the p-value is significant between gender and smoker, while for smoker and region it's not significant, or it is just above the significant threshold of 0.5%. So what does this statistical analysis adds to our exploratory data analysis? So what is the added value for going a step further and doing a statistical test? So the added value of this analysis is that it draws our attention to the fact that smoker group might be affecting the significance of the other feature, as we have discussed earlier. We have a question in mind that is not yet answered even by this statistical test. Is region actually significant, or just because the presence of high smoker group in this southeast region is what differentiates it from other regions in terms of insurance charge? So these tests confirm our earlier observation, and we also are now sure that smoker and gender are both dependent. We have discussed earlier the variant plot and said that they convey a bunch of information in a single plot. We can see here the distribution of the dependent variable being charged across the different groups, and we can see also the IQR, the median, average, and the outliers. So it's a sort of a combination between a histogram and box plot, but in a more elaborative way. We've plotted the means of each group and was questioning whether there is actual difference between the group of each mean or there is no difference. We can see here a small uptick, but we are not sure if this is significant or not. When we come to compare categorical versus numeric feature, we have two types of tests to perform. We can do a student t-test or ANOVA, which stands for analysis of variance. In a nutshell, both tests seeks to explain the variation of mean within two different groups. For example, it answers the question whether there is a significant difference, or the difference in the mean of gender group is statistically significant or not. We use t-tests when the categorical features has only two levels. Similar to our example here, gender has two levels only, male or female. and we use ANOVA test when there are more than 2 levels in the categorical feature. So in here, for example, region, we have 4 different regions. In case there are 2 levels only, both one-way ANOVA and t-test will produce the same results. There are different variations of ANOVA, and we are going to discuss one-way ANOVA. Before we dive in, we need to understand that there are several assumptions that needs to be met for the statistical test to be valid and that we can rely on their results. We are going to discuss this assumption as we go. Just don't take the analysis or the results of the statistical test for granted. Make sure that the assumptions that needs to be there for that statistical test to be valid are actually being met with your data. Sometimes we can get away with the violation of assumptions if we have enough samples. So for example, it's important to make sure that groups have equal sample size, so that if even there is a slight deviation from the assumption of each test, we can rely on the test results. And so the first step is to check the sample size of each group. So we're going to iterate over each column and print several statistics. We first print the column, then we will print the minimum number of samples in that column. We can either use dot or square bracket, but when we iterate we use square bracket. Dot doesn't work. Let's understand what does value counts mean. If we say df.gender, for example, dot value counts, I'm not sure if I have showed you this earlier or not. It groups the categories and shows the count of each category. If we selected the min, it will give us the one with the minimum value, and similarly if we did the max. So this is the minimum, this is the maximum, and this is the deviation within the group. We can see here that smoker group has unequal sample size and has the largest variation across the range of values. Just take note of this, that smoker sample size are not equal. In case we have a violation in the assumption, we should consider this. To perform these tests, the data need to be presented in a form of groups. So we have to separate to disaggregate our data into groups, and each group consists of a category and their related charge value. To do this, we are gonna use list comprehension. So first of all, let's instantiate an empty list to begin our list comprehension, and we are gonna capture the charges in each column. So it will be C. So we are gonna capture the charge value in each column in a given group. From where to get this is G, or the group, and this column we are gonna use loops. So first of all, in our list comprehension, we are gonna capture the group, and this group is located in for G in df column dot unique. Let's check what does this actually do. For example, if we df dot gender dot unique, it will provide the unique categories in this column. So we are going to iterate over these columns and capture the unique groups in this column. Now let's wrap this in a for loop. So for C in cat columns, name this groups, and let's print groups. Okay, I'm not sure why there is a red. Okay, what is your problem here? df charges df. Okay, what is this? Yeah, okay, so we can see here that it printed, this is the first group, this is the second group, so on and so forth. If you want to see only two groups, we can see break. So this column, this loop executes only once. So we can see for the first column, can see the two groups, this group, this group. So now we have our groups ready. We just pass it to the statistic calculation. Let's start by ANOVA. To do this, we are going to calculate the statistic, which is F, and F stands for the F statistics. This is what ANOVA tests, and the related p-value, and PF. Okay, this will be we'll pass the groups. If we pass groups as this, it will produce an error. We need to make sure that it unpacks all what's there in the group. So we add an asterisk, and asterisks mean that unpack everything within this list. Let's collect the results in a summary. So summary, it will be an empty list. Okay, and let's add summary dot append F and P. Let's print the summary first to check how it looks. If we append two items in a list, we need to wrap these two items in a tuple. So we pass a tuple of whatever we want to append. Okay, we can see here the F statistic and the calculated P value. And this will also in scientific notation. So this is a very minor number. It has negative 283, which means that you put in front of this number 283 zeros. Sometimes you can see here that it is positive, and positive means you add after this number this designated number of zeros. So negative or positive states where do you actually put the zeros, and this is how many zeros that you actually have to put. Okay, so let's round these a bit, and let's include the column also. So we will add the column. So our one-way ANOVA test indicates that for gender there is a significant change. It's 0.03, which is less than 0.05. The results are statistically significant to reject the null, and the null in one-way ANOVA is that there is no difference between the group of the two means, and the alternative hypothesis is that there is actually a difference. So we reject the null and conclude that there is actual difference in terms of gender, in terms of smoker. The results are also significant. They are actually significant for all of them, which means that there is a slight variation between the mean of each group. But we can see here for smoker group, it is the most significant one, and we can see the size of the F statistic compared to the other, as well as the significance threshold. So this somewhat answers to earlier that when we looked at the violin plots, we were not sure whether this difference is actually significant. Now, ANOVA comes and tells us that yes, there is a significant difference, but we still haven't tested the assumptions of ANOVA. So at the time being, we will take the results with a pinch of salt and see later whether the assumptions of ANOVA are actually being met, that we can actually rely on these numbers or not. One thing that is for sure is that smoker group is actually significant compared to the rest of the features. Okay, we have our statistical difference ready between the groups, but we actually do not know, for example for region, which group is different than the others. For these two features, we know that there are only two groups. So for gender, we have two groups, male or female, smoker, yes or no. So it is obvious that one group is different than the other. But for region, we have four groups. So it's not actually clear which group is causing this difference. To figure out this, we use individual t-tests. If you remember, we said that t-test and one-way ANOVA gives the same exact results if used on two groups. What we are about to do next is called a post-hoc analysis, which means that we first run ANOVA and identify which groups are actually significant. Then we run additional tests on pairs of groups to know which group is different from the other, treating each category as consisting of only two groups. We are gonna now run the t-test. Let's make a list t-test to collect our results. Okay, then for comp, let's write space combinations. Okay, df dot region dot unique, and we want to have only two pairs. Let's check what the combinations look like. So we have two pairs and it is not repetitive. For example, it's southwest versus southeast, and we don't have southeast versus southwest, so it's only one time comparison between each group. And let's run our t-test. We are going to basically capture each group within the combination, so equal comp 0 and the other one. Let's append this to the t-test. We will append the first region 0. And don't forget to include it in a tuple. Okay. And we are gonna use the t and pt. It's t-tests. Now let's see the t-tests. So we have each group, the related statistic, t-statistic, and the significance level. We can see here that there are significance in two groups, being southeast and northwest, and also southwest and southeast. So let's check this on the plot. Southwest and southeast. Southwest, this one, and southeast. So this one basically with this one, the last one, yeah, it's obvious that this is the lowest and this is the highest. And also southeast and the northwest. So southeast and the northwest. So it's basically there is a difference between southeast and the last two regions, or the smallest regions in terms of the mean value. But there is a problem with such test or calculation, being that as we increase the number of comparisons, and we see here that we are making 6 comparisons, at each comparison we assume a 5% probability of rejecting the null hypothesis by chance or error. So in these 6 comparisons, if we assume that we are seeking a 95% confidence interval, and that there is 5% probability of rejecting the null by chance, our p-value jumps suddenly from being 5 to 26%. And in order to elaborate this, let's assume that at each comparison we assume 95% chance of coming to the correct conclusion, which means that we do not incorrectly reject the null. So if we power this to the power of 6 comparisons, the probability diminish, because at each comparison the probability of incorrectly reject the null increase due to just chance or error. The 5% is not actually a 5% chance, and it's actually 26% significance threshold. To overcome this, we need to account for this number of comparisons in our test, and there are actually several ways to do this, or several methods to account for this. The simplest and easiest one is called Bonferroni method, and it basically divides the error rate that we expect, and it's called a family-wise error rate, by the total number of comparisons that we are going to do. So here instead of comparing the p-value of each test against a 5%, if we use Bonferroni correction, instead of comparing against 5%, we are going to compare by the following. Our threshold is 5%. We are going to divide it by total number of comparisons. It's 0.008 significance threshold, which means that none of these comparisons is actually statistically significant, which means that we are going to accept the null hypothesis that there is no difference between the mean of each group. So drastically and all of a sudden we changed from concluding that there are two statistically significant results to actually no or absence of statistically significant result when we accounted for the error due to the increased number of comparison using the Bonferroni correction method. Actually, Bonferroni correction method is the most conservative method, but in terms of our data set here and what we see here, I am actually inclined to trust Bonferroni method, because as we saw from crosstabs that it's not actually the region that's causing this significance. It's because that there is concentration of smokers in the southeast region, and this is what is making it appear to be significant. But let's keep this in mind and know that we actually have a question mark on the region feature to be considered when we come to modeling. Another method to check or to account for the increased number of comparison in post-hoc analysis is the two-key HSD. It's less conservative than Bonferroni, and in order to do this, we first import the models. And let's run the test. So MC will be equal multi-comparison. Pass our columns df.charges, df.region. Okay, so we have our test ready. Now let's print the summary. The data is actually the same. We have here the groups, and we have the mean difference across each group, and we have decision whether to reject the null or not reject the null. When it's false, it means that do not reject the null, so it means that there is actually no difference between these two groups. And when it's true, it means that we reject the null and accept the alternative, being that there is a difference between these two groups. And these two groups are actually southeast and southwest, and we can see here that it's southeast and southwest. Yeah, southeast and southwest, similar to the t-tests we did earlier, but it shows that there is a difference between these two groups only, while accounting for the number of comparisons to be made using adjusted family-wise error rate. To summarize this, when it comes to categorical for this numeric data, we are interested in knowing the difference between the mean within each group. So we do this using analysis of variance. And analysis of variance for groups that have many levels, we follow it by a post-hoc analysis in order to understand which group does actually cause this difference. And when we run the post-hoc analysis, we need to make sure that we account for the fact that we are making multiple comparisons, and this can cause our significance thresholds and confidence interval to change at each comparison. And we saw that we can account for this using two methods: Bonferroni method, which is most conservative, and two-key HSD, which use a less conservative approach. Before you run a statistical test, just make sure that you know what are the null and the alternative hypotheses that this test actually tests. Then make sure that also you understand the assumptions that underlie each test and that it's met in your data. Next, we are gonna discuss how to build a model that captures the patterns we have identified so far. And during this process, we are gonna discuss linear models and the assumptions around them. So see you there.